I'm Paul Whittock, European editor for Microwaves and RF Magazine, and I'm here on the ANSYS booth at IMS. With me is Matt Cummins. Matt is the lead product manager with the company, and we're going to be talking to Matt about the company's HFSS technology.
Hi, Paul. Thanks.
Hi, Matt. Thanks for joining us today. Could you give us an overview of your HFSS technology, please?
Sure. HFSS is a 3D electromagnetic field simulator, fundamentally based on a technique called the finite element method. The finite element method's been around for a number of years. HFSS itself really made its name in providing very, very accurate solutions for many types of waveguide structures, microwave circuits, etc. Its success was predicated on adaptive meshing, so the engineer doesn't have to interact with the mesh and understand how to mesh. Now, since then, it's expanded to more types of solver technologies, more types of solver techniques. We've improved the GUI experience. We've made interacting with the software much easier for the everyday engineer who isn't necessarily an expert in electromagnetics.
Thank you for that, Matt. Now, I know you've got demo units here, and why don't we go over and take a closer look at those?
Okay, sounds good. All right, so what we're looking at here is a new feature we will be releasing in HFSS 14 later this year. It's a finite array analysis tool. In antenna array design, one of the big challenges for simulation is trying to model these very, very large arrays. They're geometrically complex, they're very large, so they're very computationally intensive. We introduced a technique in version 12 called domain decomposition, and in this finite array tool, we've leveraged some aspects of array design to make that technique even more efficient. We start with analyzing just a unit cell of the array. This is a skewed rectangular waveguide array, 256 elements in total. We analyze just a unit cell, we mesh just a unit cell, and then we virtually repeat that mesh as many times as required to describe the entire finite array. And then using the domain decomposition method and as many compute engines as you can apply to the problem, we can solve all the individual cells in parallel and then iteratively reconstruct the solution for the full matrix on a host machine. It's a very efficient technique for solving these types of complex geometries. It's very parallelizable. You can have multiple machines running this one design in parallel, and so it can be very, very efficient. And what comes out of the whole design is you can get, for example, the 3D radiation pattern, 2D pattern cuts. You can get the full S-parameter matrix, all 256 elements, including all the coupling coefficients, etc. from the design. Edge effects are included, so the engineer can understand not only how a cell behaves in the middle of the array, but even understand how ones behave out on the edge. Okay, next I'd like to talk about something we actually introduced in version 13, and it's getting a lot of traction in the market, and it's known as finite element boundary integral. Finite element boundary integral is a hybrid solver technique where we're using finite elements in certain regions of the design and then integral equation or method of moments in other regions of a design. In this example here, what we're looking at is we're looking at a helicopter with a parametric study of the rotating blades of the helicopter. And if you look closely, you can see this red wireframe box that sort of conforms very closely to the rough outline of the helicopter. And this is sort of new to people who have been using HFSS for years. You can have, in effect, with this box, a very conformal air volume that wraps right around the geometry. In fact, you can even have that conformal volume move with your geometry, as we're showing here. And to solve for the free space condition for this model, we use an integral equation or method of moments solution on the boundary of the air box, but still use the rigor and accuracy of finite elements interior. And again, use an iterative technique to resolve the solution between those two domains. It's very efficient, extremely accurate. It's a very accurate solution to the free space Green's function using finite elements. One other interesting aspect that this animation shows is you can have physically separate domains. In this case, if you watch the animation, you'll see that a missile launches out of the helicopter, and that missile itself has one of these conformal air volumes surrounding it. And this is all encapsulated in one single simulation. You've got a finite element domain around the helicopter, one around the missile, and then of course it's all being parameterized and modeled with respect to the rotation of the helicopter blade. Very efficient. In 14, we're going to extend this where if that missile is entirely metal, you don't have to have the surrounding air volume. You can use an integral equation solution directly on the conducting surfaces of the missile. A great example where this could be used would be, say, in a dish antenna analysis, where you could use HFSS for finite elements for the horn feed, and then an integral equation solution for the dish. Okay, the last thing I'd like to talk about is our new electrical CAD or layout interface for HFSS. Many electrical engineers are not comfortable working in a 3D design environment like you find with HFSS. However, they are familiar with layout environments, as I'm showing you here. In a layout view, you're looking at the structure top-down. In this case, it's a bandpass filter design with a spiral inductor and a tune cap. In this type of design, you have layers of dielectric, layers of conductors. You have concepts in this framework such as a stack-up, as we have here, where we have layers of air, dielectric, signal, etc. But ultimately, especially in modern designs, these designs, which years ago might have been tackled by a 2.5D code, such as a method of moment space code, now need the rigor of a full 3D solver like you have with HFSS. So in such a design, we really do have 3D entities. We have thick conductors, we have test fixtures, etc. So we really need the rigor and accuracy of 3D. This framework, built in ANSYS Designer, allows an engineer to set up a layout-based design. They can also import it from CAD tools such as Cadence or Mentor, and easily set up the excitations, the simulation, and everything, and solve directly from the designer interface with the HFSS solution engine. So it's a really easy entry point for engineers who are comfortable working in layout and want the accuracy and rigor of HFSS.
Matt, thank you very much for that. That was a great demo. Now, for the engineering viewers of Engineering TV, could you give us a web address where they can get more detail about your company's products?
Sure. www.ansys.com, and ANSYS is spelled ANSYS.
Thank you very much, Matt.
All right, thanks.